waiting for the master lecture, which will be delivered by West Church. The title is Predictability of Behavior.
Well, thank you very much, John. I really enjoyed that symposium. Listened to all these wonderful things that were said about me. I think in the interest of balance, I should say that not everyone shares those views. In thinking about evaluative profession, I thought of the Harry Harlow, who was editor of Journal of Comparative and Physiological Psychology at a time when I was a graduate student trying to publish a research paper. I remember the letter we got, which said that in the discussion section, the two-process theory that was used was awful and should be eliminated. It was a mere repetition, in other words, of what was said already in the results section. But it's not just editors. There are these grants that you send in to try to get some funds. And I do remember an anonymous reviewer who wrote some years ago that his contributions, that's mine, to theory have been minimal. These are the things that you tack up on the wall like people in sports do and see. First you get angry, and then you get rational and figure out why the person who's criticizing you is wrong. And then after a while you think maybe there's a kernel of truth. And in the long run you become better, I think, more because people criticize you than they praise you. I find that also in teaching evaluations. I actually save mine. I save all this. I have file cabinets full of critical material. And the kinds of things I remember is lectures, sometimes just single words, usually in capital letters and rather large letters. Boring, disorganized. So I will try to do what I can, but what I mostly wanted to do at the beginning was to lower your expectations. So at the end of this lecture, you will say, that was better than I expected. So the topic is the predictability of behavior, and I'll begin with some acknowledgments. First to my current collaborators at Brown, Paolo Giorgi, Nicola McGinnis, Lil Yee, and Marcelo Quintana, all of whom are here and who have presented, and they are responsible in large part for the empirical and theoretical talk. Also to the National Institute of Health, who's a loyal supporter of the research that about. I'd also like to acknowledge previous contributors at Brown, because they are the ones who established the real basis for this talk and who now continue. And finally, to other people who may not all of them appreciate that I consider them the investigators of finding, but many of them clearly are, and all of them have major influence in my research, and they're very far from this. Well, first of all, about that disorganization. Look at that for organization. The outline of the talk is to begin with a rhetorical question. How well can behavior be predicted? and you know the answer is going to be number 6 very well. And so it's sort of like a detective story where right at the beginning you know who committed the murder. The question is, how did he catch him? And so that's 2 to 5 is really the important part. What does it mean to predict behavior? What kind of example may we use where this was done? What kind of model might one use to do this prediction? And how would you evaluate that model? Well, then, to begin, how well can behaviors predict? Well, one view is it's not really possible. Because maybe behavior isn't determined. We just act as if it is so we can get some work done. But really, people and animals have free will, or at least a little free will. And maybe there's sort of an environmental free will also, which is called their random factors. Is this a serious philosophical question? Well, I went to the internet to try to get some information about these matters, and in my view, probably behavior is determined by biology and experience. Maybe that's a good hypothesis. But free will probably is just an illusion, and a book by Wagner is really very good on this. But the beautiful thing is, as shown in Popper's chapter in Causal Determinism, that it is a very reasonable notion to separate the idea of how predictable behavior is from either the truth of determinism or free will. That is, just because an animal has free will to do what it pleases, we can predict what it'll do because we figure out what it wants. So I'm not worried about animal free will. And similarly about determinism, some deterministic systems are really hard to crack, like what we use for codes, for example. But some non-deterministic systems can be predicted very well if you define prediction well enough so that if you predict something's going to be random, and it is, you got it right. So we'll get to that. But the standard view is, if it's not impossible, at least it's very difficult for us, because we aren't very smart. We're just psychologists. And our science is too young. It's not, many, many centuries old, really, only a century and a half, but it's pretty long. You'd think by now we'd have it right. I think at some point we've got to give up the idea that we can't do it because we're not mature enough. The standard view is, well, even if it isn't difficult for us, particularly if it's difficult for anybody, because we're taking on a really difficult problem. It's the problem of determinants of behavior, but they're determined by the brain, and the brain is very complex. Or alternatively, that is determined by the environment, and it's very complex. Or even worse, maybe it's determined by both of them, and they are doubly complex. So, my view is the problem can be stated in a way that's very simple. I talk about it as Skinner's problem. It's sort of like cooking. You've got ingredients, a wrap, a box, some stimuli. You've got a recipe or procedure, and all you want to do is predict the response of the wrap in the box. Procedure includes a few stimuli like light, noise, clicker, and a reinforcer. Food, the response could be the head entry response, lever press, looking, exploring, grooming, Today, I'm only going to be talking about the procedure variables on the left and head entry as the only ones on the right. Now, the key to making this a solvable problem is to define predictability very carefully. If one thinks of you predicted it, if you've gotten the exact time of the response to the millisecond, it'll be impossible. If it is possible, try microsecond. The notion is that is not the goal, to have an absolute prediction. But secondly, you can go wrong in the other direction. You can say, I have a prediction which is better than the alternative, and then pick a really bad alternative, like the null hypothesis. The variable I've manipulated isn't going to do anything, and it does, and you say, see, I'm right. That's the bad. That's not two. But number three, that's what we'll be doing. And I think that's just right. The notion is you can make a prediction of what a rat will do if you have seen what the rat does in similar conditions in the past. And so basically you are saying, I bet I will get what I have seen before. And what you try to do is to predict not from what you have seen the rat do, but rather on the basis of the input you make, the procedure. And that's where the Turing test comes in, is when you have both the known procedure and the observed behavior, see whether the procedure does as well as other examples of the behavior. Well, now let's try to get this a little more concrete. Let's look at a rat in a box for a few minutes and see what it is we're trying to predict. So here's the rat, and it is now exploring the bedding, the grid in this little box. It responds now going over to the water tube and is drinking the water. And each of these behaviors seem to last for a little while. They are rather cloudy. So that there's just quite a number of frames where the animal is drinking some water. We have been exploring. What will it do next? Oh, it goes over to the food tray and is examining it for whatever. So head entry, every time it puts its head in there, it breaks a photo beam. And now it is exploring a little bit more, and now a bit of grooming, face grooming. You pause, but then we'll continue the grooming act. Coming up over the ears, generally, in this clip. And body and back. But you get the idea. Moving around. But all we're looking at in this will be when did it break that photo beam at the food truck. So what we have here is a rat and a procedure which has really not begun there. That is, the experimenter did not have intervening events like turning on stimuli, dropping in food, and so on. But the procedure could give to the rat stimuli and reinforcements, and the rat can give to the procedure responses. And everything that occurs can be recorded, the observed data, as times that various events happened. And so to look at this in more detail, we have here time. This is just from one cycle of a fixed interval 30-second scheduled reinforcement at some time from the beginning of the session in seconds to a resolution of 2 milliseconds, events occur. These events have an event code: 17 for the house light on, 8 for a head entry response, 27 for house light, 19 for food delivered, and so forth. In this particular case, we just calculated the relative time relative to the house light being on. The first response was at 27 seconds, pretty close to the 30. And then there are a whole series of 10 responses before the 10 seconds, and then one at 30 seconds. The house light goes off. But the notion is the primary data that we'll be working with will be the times in which each of these events occurred, not summary measures of all of which can be based on these data. Now, if we had a model, and of course the model is coming up very soon, it could do the same thing, a computer model. It can receive stimuli and response information from a procedure, the same procedure as controlling the behavior of the rat, and it can send response outputs to the procedure. And then we would have a predicted data of the same form, time event codes from the model that could be directly compared, observed to predict. You had a model that didn't like the rat, so you couldn't tell which was which, then that's what we're aiming for. The general approach is that there are certain parameters that need to be estimated. They can be estimated based upon having a procedure, a model, and some parameters there. They can be found either by simulation or by explicit solution. Simulation is what most people do most of the time. It's easy to do, but time-consuming to execute in large amounts. When possible, explicit solutions are highly desirable. John Gibbon had done a lot for scalar timing theory by coming up with explicit solutions. Mondo Machado has done the same for LET, and I'm very much indebted to Lyndon Lee, who has done the same for packet theory, and what I've been describing will be using the results that she has, which has made it possible to do things very quickly. The general idea is the same between simulation and explicit solutions, except a simulation requires, say, if you'd like to know what happens after 1,000 trials, you have to know what happened on the 999th trial. So you go from 1 to 1,000 multiple times. Whereas here, n is just an independent variable, 1,000 as well as your other parameters. Okay, so here's a particular timing experiment. It's the multiple cube interval procedure that has been developed by Ology that we have made a great deal of use of, which is having 3 different stimuli, noise, light, clicker, associated with 3 different intervals, here 30, 60, and 120 seconds. That in a particular experiment, these would be counterbalanced, but for illustrative purposes here, we can keep it concrete. The noise goes on for a 30 seconds. The first response after that, the first head entry response is food, and then a random permutation of these is done so that would be noise, flicker, and light at 3 different intervals at 2 different amounts. Now, I'll just quickly show 4 typical summary measure results from this procedure. The thing to gather from this is, well, all of the data seems very clean and smooth. And the other is, each function looks very different from the other functions. And the reason I'm doing this is to indicate what the theoretical problem is. It's not to fit a particular curve, because the curves look all very different, but it's rather to fit the behavior of the animal at the primary level, so that these dependent variables and any other dependent variable that one could concoct from the primary data would be fit by the model. So this is the familiar gradient. The time since the stimulus onset, which would be 30 seconds for this one, 60 for this, and 120 for this, is the independent variable. The dependent variable is response rate divided by the maximum response rate. And the reason for doing that division is to equate them all at the top, so that this is a measure of pattern. It tells you nothing about rate. So this is a measure sensitive to pattern. Now, here's another one sensitive to pattern. It's the same idea, except it's not time from the beginning of the stimulus. It's time from some response criterion of when the animal shifted from a relatively low response rate to a high response rate, and it's averaged forward and backwards. And again, relative response rate, and it's relatively flat with a big jump, and then relatively flat again. Much the same for the 30, 60, and 120 in terms of now here's response rate, which is just a familiar bar graph for the during the 30-second stimulus, during the 60, and during the 120. And you see the error bars are rather small, so that this would be a highly significant difference, having the inverse relationship between interval duration and response rate. And finally, the inter-response time distribution, which is plotted here, relative frequency on a scale of inter-response time in log base 10 seconds. So that a 0 would be 1 second, that's 10 seconds, it's 10 per second, and so on. Note that the functions here are all much alike for the 3 intervals. The IRT distribution is not affected by this procedure, which simplifies things a lot. And it looks very, very pointy distribution. And those are the 4 very different shapes that we have in this example to try to reproduce. So here is a theory, and we'll try to get it to work. Packet theory is just another one of the many timing theories that can be applied to data of this sort. There is a time marker, that is the stimulus onset, a clock, 2 kinds of memories, one called pattern memory, one called strength memory. This is one feature that is distinctively important in this theory. And there is a decision that is based upon information from the 2 memories at an operative level, and the outcome is, rather than a single response, a packet of responses. one go making up some new theory? Well, the usual thing to do is to take excellent features of previous theories and maybe add a little thing here or there and come out with one that might be intermediate. From scalar timing theory, clock is an accumulation process, threshold for comparison is being used. From running to time, Machado's 1997 model, using linear operator model for memory and perception and memory as vectors are being used. And other sources for having two separate memories, one for pattern, one for strength, and having response bouts, and finally incorporating operant rate. I think those are the essential ideas that are used in what I will show next, which is a fuller flow diagram of what packet theory is. It's so small, it's got so many parts, there is really no chance that you'll be able to work your way through it if we use this figure. But if I break it apart, showing what perception is, what memory is, what decision is, and what the response is, it probably will be at least intuitively plausible to you. Perception. We have a time marker which will start a clock. The clock is this accumulation process, just goes up. So T is physical time, T prime is psychological time. When a reinforcer occurs, the whatever is in the clock gets flipped and is called a perceptual store, and that then becomes the output of perception. Let's see what we can do with this perceptual store. Intuitively, this is time since the cycle began until the food on what has just happened. There's the perceptual store that got updated by the reinforcer. Now we're down in memory. This goes to pattern memory. The perceptual store gets combined with what's in memory by a linear operator model. Basically, some percentage of what is already there and this. Generally, it's a small percentage. This is thresholded so that it moves memory into two states. One is low and one is high, zeros and one. Meanwhile, in strength memory, whenever a reinforcer occurs, there's a big increment, and whenever reinforcement is not occurring, there is a small decrement. Okay, these then are the two outputs. How shall we use them in decision? Here they are, pattern memory, strength memory, go into packet initiation. Something else is coming into packet initiation, which is operant level. So, oh yes, you may have noticed there are things called equation 1, 2, 3, we're now up to 8. I'm not putting the equations here, but they're sort of obvious from the pictures, and what you think they would be is what they really are. They did that, a lot of symbols. And so equation 8 would be essentially a combination of these three, which operant level lifts this over off the baseline, and this essentially gets copied here, the big step here, and the little decrement here. Now we have packet initiation. What do we do with it? We send it down to a packet of responses. What's the distribution of the packet of responses? You've probably seen this in the data, and we put it right here, which is the Laplace distribution back exponentials on a long scale, an approximation to what the neurons are actually doing. So what can we do with this? Well, this now, the data points that you've seen before are going to be shown again. Here they are. The line, however, is from packet theory. It's the best fitting parameters, and those lines are 3, 4, 5, 6, 7, 8, 9, there will be 12. And there is the last one. And all of the individuals are well fit by packet theory, but you will notice that they are different themselves in some ways, so that there are large individual differences, but within each of the individuals, they are following the same rule that the mean does. So that's it for the response gradient. These are the 12 individuals. Now, this is the average for the lining them up by the time of the transition, the average, and the individual. Once again, you see the packet theory fits pretty well. The individuals, there are some systematic deviations, but and they are very different from each other, individual differences, but the same rule seems to be pretty good. Thirdly, this is what you've seen for response rate. Let's see what the model did. This one, and there it is, the model with its red standard errors in bars show that it fits the response rate. This is the inter-response time distribution, the bouts, and this is the mean data that you've seen before. Now let's see what the individuals look like, and here they come, one after the other. We're at 3, 4, 5, we'll be up to 12 very soon, and then the model fit will fall on top of that. And there's the model. So the IRT 30 looks pretty good. And what about the 60? I won't bother going through all the individuals, but you can see the individuals there. They're the black, the mean is the red, and the line is the model, and the 120 is also the thing. So the idea is to try to fit very different summary measures and not have them particularly selected for particular advantage. Now, how do we go about evaluating a model of this sort? I'd like to make a distinction that is made in this slide. If we divide the data into two parts, such the odd trials, the odd sessions, and the even sessions, and just do percentage of variance accounted for in R square correlation squared, it's very high. That is, the animals are quite reliable from one set of sessions to another. To the extent that it's not one, that is the extent to which there is random variation here. So a very small degree of random. The predicted data is based upon packet theory with parameters estimated from what's called the calibration sample. But the key way of evaluating the model is to take the predicted data from the part that wasn't used for estimating the parameters, the observed data, the validation observed data, and see how much lower this is than the random variability. And what is here is the extra error. The fact that this is lower than this is because there is some inexactness in the So that one can come to a notion of how far off the model is from looking at these two. But if we work with these two, we're getting a higher amount of error, because in addition to model and random, there can be some overfitting. Because people say, oh, we've got an awful lot of parameters in this model, don't you? Isn't that just capitalizing on chance, this sort of thing? In general, I think the answer is going to be no for any time you try to fit high-quality data with small amount of variability, because there isn't much random stuff to erroneously fit with extra parameters. But it's a nice thing to check, and the method is called cross-validation, and I think it is probably the easiest and most intuitive of the ways of providing some confidence that you're just not fitting noise. Well, a Turing test is one in which one has a known source, say the rat, for some of the data, another known source, a model for some of the data, and you take an example from the rat, an example from the model, like one cycle, and then an unknown sample, and determine whether this unknown sample is more similar to this one or this one. It has to be a yes/no decision, one or the other. So if the comparison is more similar to the rat, you say it's a rat. More similar to the model, you say it's a model. If a model were perfect, you can only distinguish it half the time, chance. If it was awful, you could distinguish it every time, 1.0. And in 1950, when Turing described this Turing test in the journal Mind, he had this wonderful quote. He made a prediction 50 years in the future. Well, that's long past now. Thought that it would be possible to program computers with a storage capacity of about 10 to the 9, yeah, we got that, to make them play the imitation game, this kind of game, so well that an average interrogator would not have more than 70% chance of making the right identification after 5 minutes of questioning and so on. In other words, he wasn't thinking that for the problem that he had was, can I tell if the thing I'm talking to that's sending me written messages is a computer or a person. He wasn't thinking that it was going to be that great. It would have deficiencies, but it's a nice test to see how well you can do. Well, how well can we do it now? Here's an example. The data that is used here is just a sample of one 30-second cycle in which the times of responses are transformed by reciprocals into 1 over the interresponse time, that is a measure of local rate, until the next response comes. And then, so you have a local rate of continuous function at all times. And then we just take the sample and see whether it's closer to the rat, which is coming up here, or the model, which in this particular example came up here and here. And in this case, we said the sample was a rat. Well, of course, a computer does this real fast, and so it goes through a huge number of them. We just say the percentage of time you got it right. In this particular case, we got it wrong. But how often do we get it wrong on average? Well, it's not 50%. It's closer to 60% correct identification. And so that means we're about 10% away at this point from perfection. I think with some improvements already we're down to 55, and the goal is each year for another year or two, and then move on to something else. So the answer, we say, is quite well. Well, you do that. And so I can now just end with a summary. And the summary goes that behavior is quite predictable, at least it is for a rat. I don't think there's anything special about a rat. I think other animals, maybe even people, would be the same. But it is in a simple environment, and that makes it a lot easier. The simplicity of the environment, I think, is very, very critical. But if you have it right, it should scale up. If you have the laws of motion, you might be able to get a rocket to the moon. We use just 3 conditions here. We've used it for other applications elsewhere. We think that procedurally is quite broad. We had 3 types of measures of behavior here: pattern, rate, and bounce. That could be extended more, probably. And we did it, though, for individual cycles, averaged across cycles, individual rats, averaged across rats, and I think that's very important, is to be able to do those. So what's needed? Well, I think it was important to have reliable measures of behavior, that is, to have behavior that really is and secondly, it's good to have a plausible model that makes good use of what other people have found out, and add the things when things aren't fitting to see that it works. And then finally, a way to compare the observed data with the expected data in a quantitative way. And the goals now, for us, I think, will be to increase the generality, to ideally extend it to all procedures in a specified universe. And that sort of thing can be done by sampling maybe. And again, extend it to all summary measures in some well-defined way. And then even to extend it to all observed behaviors. Remember that little film at the beginning? The rat was doing a lot of things besides breaking that photo beam. And the poster they provided support for the idea that one might be able to do types of grooming and exploring as a decent measure. And once you have it as a measure, you can have it as something to predict as well. We should improve the fit. Some places, the discrepancies are small, but they're systematic. And systematic discrepancies should be removed because it could be something fundamental, such thing as, well, the clock really isn't linear. It's an oscillatory mechanism or something of this sort that could lead to further improvements. Whenever possible, decrease the complexity. And then it'd be nice to find some productive uses for this sort of thing. 3 possible ones would be wonderful in secondary data analysis of archived data. This is a place that we archive data. I can strongly recommend the Psychonomic Society's archive of forms and data as a place to go. I hope people really use it. When you have some good data, share it with everybody else. You published, you're not going to look at it again. But this, for example, is all things on the Psychonomic Society data set. And it's something that it has lots of rat drinking that we and nobody else has looked at yet. And it's a shame to spend a lot of time and money collecting data reporting one thing and then basically throwing it out or throwing it into your file cabinet where nobody can find it. But it is one productive use for good theory is to be able to see these information applies to existing data. Second is it may help in, we should move towards unification of related topics. We have separate theories for conditioning, timing, choice. Maybe that's a mistake. Maybe more common theory will handle them. And finally, and very importantly, making some novel predictions. It's easy, especially with explicit solutions, to say, well, I wonder what would happen if I did this experiment. It doesn't cost you 6 months. It maybe costs you a few hours. And if you find something that's surprising, you say, oh, that might be worth looking at. And anytime modifications are made in a model, I think it's very important to be sure it's backward compatible, because you don't want to change the model for a particular data set if it's messing up all the other predictions you made next. Well, it says that's the end.
Let's say I look at a lot of birds' nests, and I kind of how they're constructed, and I go out and construct one such as birds nest is far apart from its own nest, for example. But the processes I use to build that nest might probably be different than the one, maybe not, it might be different than the one the bird used.
Right.
Is that possible if a model passes a Turing test for an identification or discrimination by a computer, that still the model is a different process than what's going on in the subject?
Although Alan Turing is a god in the field of cognitive psychology, Turing is basically a behaviorist. And the question you asked me essentially is the behavioristic criterion right? Or is there something more fundamental that is doing it? No, I absolutely agree with you. It's a matching of input and output. It's not matching of the internal mechanism. If you can make something that is indistinguishable from an automobile, even if you use entirely different principles, if nobody can tell them apart, I call them an automobile. But you're right.
Because differentiating them allow mechanics to look under the hood.
Actually, that's right. It depends upon the test you allow. And there may be tests that will discriminate. And if there is a test that will discriminate, then you say it isn't. So the problem really is, how good is the testing? And I say, well, I use the 4, but what if there were others that would do it? Yeah, I agree.
Another rather general question.
Yeah.
I wonder, as a biologist, very often the question one asks is not just how the animal is built and what the processes are, but why are those processes that way? What good is to the animal, for example, to have packet theory in its mind, or whatever it is that it has. And what I would like you to perhaps to reflect on is whether among the goals of your theory you would include some relation to normative problems and some relation to the normative kind of questions. And how would you go about that? I mean, how would you ask this page, why is it that the animal is doing things in that particular way? Or how else could it be done?
I think that this approach has nothing to offer to either function or evolution, how it came to be here. That is, I think that this is just isn't suited for those questions. Other methods have to be used.
Has got something to gain from it if you can't use it anymore. So can you think functionally to improve in the lines that you want?
Possibly. I mean, where the ideas come from, one doesn't know. Where did operant rate come from? And what maybe one would like to explain why the operant rate is what it is, and so on. Right now, it's just a free parameter, something to be estimated. So I think there always is the deeper question. You start somewhere, make these assumptions, and then you get this output. And you can say, but can you tell me more about where that assumption came from? I think one can do that. So that obviously this is not complete.
Ralph will have the last question.
If the calibration data session is structurally no different from an observation data session, correct?
Yes, that's right.
Forgetting the process for a moment, effectively the calibration session, you're photographing the behavior, capturing it in the parameters.
In the parameters, yes,
And
that's true.
if one forgets about the process, isn't the prediction of the model effectively playing back the very same observations and assuming consistency of the data from the observation session, from the calibration session to the observation session?
I think that technically what it amounts to is with the model you have greatly reduced the degrees of freedom in your prediction. That is, if you had, let's say, take a small number, 100 data points, and you said, I would like to predict them, the best predictor would be to return the same 100 points. So with 100 or 99 degrees of freedom, you can predict what you got. But what one is doing is cutting way back. If you could predict the behavior with only the procedure and no estimated parameters, that would be the ideal. But as you increase the number of estimated parameters, you just want to keep it way, way down relative to the number of data points you predict. But yes, one can do better, and that's why reducing complexity should be one of the aims.
So we'll have two more.